And in classical column theory, there are few assumptions, and I only list the 6 most important ones related to this class or related to structural stability, the buckling of columns. The first assumption is we have to assume that columns are perfectly straight. And why the columns have to be perfectly straight? That's because the geometric second order effects will not be considered. That's why we said perfectly straight columns. And similarly, when we say there's no eccentricity, that also means that second order geometric effects will not be considered. The same idea. But perfectly straight columns is not necessarily no eccentricity. These two are different. And no eccentricity means the column really have to be straight. And even is tilted at different angles, but there cannot be any change of the geometry throughout the entire cross-section. But when we say perfectly straight column, that means the column has to be perpendicular to a level ground. That's the idea. That's what perfectly straight means. In other words, you may have a perfectly straight column like this, but you cannot have it tilted at any angle, even if it's perfectly straight, right?
Hey, leave it alone. Kona, leave it alone.
It looks like Cassandra is having some trouble at home. And the
I'm so sorry, my mic is on.
That's all right.
My dog's being a brat.
I know that kind of troubles. The third assumption is the plane remains plane. And this actually has something to do with shear deformation. Plane remains plane means when there's a deformation occurs and the warping of the plane will not be considered. And plane remains plane is usually true for small deflections and is usually true for linear materials. So plane remains plane is essentially the combination of the following 3 assumptions, which is no shear deformation is considered. But when we say no shear deformation is considered, that means the deflection of the column is mainly due to bending, not due to shear. Real column bending actually has 2 components. As you know that when the column starts bending, there's always moment actions and also shear action. By assuming that shear deformation is not considered, all we have to consider is just moment. And the 5th assumption is called linear materials. Well, linear materials not necessarily has to be elastic material. That's the power of classical column theory. You should remember that from strength of materials. Linearity and elasticity are 2 different things, right? There are 4 different combinations. They could be linear elastic material or linear plastic material, or nonlinear elastic material and nonlinear plastic materials. That's the 4 possible combinations we can consider here. And in classical column theory, linear materials can be applied. The last but not least is called small deflection, and that is just for the ease of mathematics. Once you have small deflections, everything can be simplified to a more manageable expression, which engineers would love to use. So with that, we're going to start with the first example, and that is this. Okay. We're going to start with the first one, and this is already page 20, I presume.
This would be example 7, I believe.
Thank you very much. You're right. Example 7. So now in example 7, we're going to study the buckling of an eccentrically loaded column. So what does that mean? That means there's a column, looks like this. And the column is supported by a pin and a roller, which means there's a hinge support here, and there's a roller support here, like that. To include eccentricity, we're going to add two little pieces at both ends of the column. So one way to do this is to add something like this. There's a small piece here, another small piece here. Now, to introduce loading, we're gonna do something like this. We're gonna apply the force, not at the support, but at the end of this little piece, which is like this. Now the distance or the length of this little extrusion part, we define it as regular E. So we said this thing has a length to be E. Of course, the same length at both ends. Like this.
Professor, that length E, that's like a flange type of thing, right?
Yes. You may consider that as a flange, but also it's really not a flange. You can consider that as more like some extension part, perpendicular to the original length of the column. And everything else remains the same. The total length is still L, and the columns still have E and I, like this. Now, what do we have to do? The same thing, we have to find out what is the critical load. So how do we start? Well, you know that we have different choices, right? If we recap a little bit, what are the options we have in finding the critical load? You can go with the force approach, and the force approach is also called bifurcation approach. And the second approach is the energy approach, right? By relating the total potential energy with the difference between potential energy external work. That's energy approach. The third approach is for dynamic stability, and most likely we're not going to use it in this class. So it's either force approach or energy approach. Now, depending on individuals' comfort, I mean, some people feel comfortable using force approach, others may like to use energy approach. When it comes to exams or homework problems, unless the question clearly specifies which approach you should use, otherwise it is your own liberty. You can choose whatever approach you feel comfortable. On the exams, especially when it comes to the PE exams, in most cases, I said most cases, the question will not ask you to use certain approach to solve the problem. Unless there's a problem, they want to know that, do you know energy approach at all? Then the approach will be specified. So here, I'm going to start with the force approach because that's most people are familiar with. So we start with the force approach. Again, one thing you already noted is that the way we solve problems must be in the step-by-step manner. You always have to solve problems in steps. Do not just start scratching around. Start with your conditions. So first of all, what do we know? By using the force approach, we said we're going to use force approach. And to do that, we need to have the free body diagram. The free body diagram, of course, we can take from both ends. Suppose one end is A, the other end is B. And again, another suppose. Suppose I want to look at this end. For the free body diagram, like this. And this is how it looks like. After the deformation, the column is going to bend, something like this. While the hinge is still here. Of course, actually we forgot perhaps the most important thing, that is coordinate systems, right? We had to define our coordinate systems. Now, with this kind of application, you know that the column is going to bend toward the right. Therefore, it is only customary to make the deflection to be positive. Therefore, positive x and positive y will be defined this way. Along the longitudinal direction of the column, there's always the x-axis direction. And the perpendicular direction is going to be the y direction. So this is y. Therefore, at point A, we have this. This is y, and this is your x. Right? Now, let's not forget about this piece. Which will be like this. Because of the right angle, should be preserved like that. And the force, of course, we're going to have the force P is here, and the internal action is going to be like this. There's another P, right? One is action, the other is reaction. Now, to simplify the problem because of the small deflection, we're going to assume that the distance between the P and the support A is still E. Even so, we know that that's not exactly E, that should be E times cosine theta, right? However, we're going to simplify, so we're going to say that this distance is actually E. Approximates to E. Even so, it actually should be E times cosine theta. And what's the theta? Theta means this angle is theta. Okay. Now, of course, if we want to take the moment equilibrium, we know that the internal moment should go like this. So this is the internal moment. Right? Now, what else do we have? Well, what about at the support A? Do we have moment at support A? Yes, we do, because of eccentricity, right? So force P is the action, right? And the reaction at A, we have not specified it yet. The reaction at A is actually, there's a force P here. And there's also another moment produced by this force P, which is P times E. Would you agree? Correct? Of course, it should be P times E cosine theta, but we said we're going to simplify the problem, so we take it as just E. Therefore, another moment at here is going to be this. And this is just P times E. Correct? Now, the moment produced by this internal moment, however, is not just P times E, because don't forget that there's another distance, which is from here to here, right? That means what? That means when you consider the internal moment is not just P times Y, and this distance is, we call Y, that's the variable Y.